Okay, hello again. Let me introduce Professor Ahmad Qudsi, chairman of this session. Camera, yes, hear you.
Okay, thank you. By the way, Elias will upload his his most recent PDF file. Can you open him?
Hello, Elias, are you there? Can you hear?
Can you hear me?
Yes.
Okay. How can I upload the PDF file?
You can do the test. We tested it yesterday. You can do the same.
Share document?
Yes, you can.
Click on share document. Okay. All right.
I deleted your previous file, so you can upload new one.
Okay, I can see the file. I don't know if everyone sees the file.
Okay, Beno, can we start now?
You are boss, Ahmed.
Okay. Welcome everybody to the afternoon session. Our first speaker is Elias Kiritsis from University of Paris Cité and University of Crete in Greece. He's going to talk about holographic QFTs on AdSd, wormholes, and holographic interfaces. Elias, please.
Thank you. Thank you very much for this kind invitation to present my work. Do you hear me well?
Yes. Go ahead, please.
Okay. The topic I'd like to discuss today is holographic quantum field theories on AdS space and related wormholes and holographic interfaces. This is work, just a minute, let me see how I change. Yes. This is work that has been done in collaboration with our chairman today, Joel Ghosh, Francesco Nitti, and Valentin Nouri, and it's also based on ongoing work with similar authors. So let me start with an introduction. What I would like to address today are, generically speaking, two problems. One of them is the dynamics of quantum field theories on AdS space, and the second is the notion of proximity in quantum field theory, something that I will explain in a moment. As we are going to see, the two problems have a common area where the techniques overlap, and this is why I would like to discuss them first. So let me start with quantum field theory and AdS. This is a problem that was first seriously addressed by Callan and Wilczek in 1990. Their interest was in infrared physics, and the motivation was that if you consider theories like QCD, there are many infrared divergences that plague QCD perturbation theory, and therefore perturbative calculations are very difficult to handle because of this. A little bit later, in fact, with Kostas Kounas, we have done something similar to this for string theory, because there also the only divergences that exist are infrared divergences. And the reason that AdS space improves this is because of its property that even for massless fields in AdS, the propagators vanish exponentially at large distances, like if you had massive fields. And the reason, of course, for this is that if you consider the Laplacian and other relevant operators in AdS, they have always a gap. There is also a related issue that appears in general in critical systems or massless systems. So critical systems are known to be described by mean field theory only if you are above the upper critical dimension, and therefore you can do easily perturbative calculations. However, if you put them on AdS, AdS acts in a sense as an infinite dimensional space, and therefore for critical systems, the critical fluctuations are always weak in any dimension. So generically speaking, AdS is expected to quench strong infrared physics if there is one. And an extra ingredient is that quantum field theory and AdS must realize the AdS symmetries, and the AdS symmetries is like having conformal invariance in one less dimension. So it's more or less the same symmetry you would have had in terms of generators as if you were on flat space. It was also noted that the structure of instantons and their dynamics is expected to be different if you put a gauge theory on AdS. In flat space, in QCD, we expect, since the work of Witten in the 80s, to have an instanton liquid rather than a dilute instanton gas. And only if you go above the deconfined phase transition, you expect an instanton gas. However, in AdS, you expect always an instanton gas independent of the phase. There is another also characteristic of AdS, that is, if you have a theory with fermions, then chiral invariance is always broken by boundary conditions, and this brings to forth something which is very important when you put quantum field theories in AdS. Boundary conditions are crucial in what eventually the dynamics will be in the bulk. So let me, for example, describe what you would expect for a confining gauge theory on AdS4. This is something that has been discussed in the past, qualitatively at least. In that case, generically speaking, you have two types of boundary conditions. You have the electric, so-called electric boundary conditions, which are basically Dirichlet, and the magnetic ones, which are basically Neumann. With the electric boundary conditions, gluons are allowed inside the AdS. They are gapped, as I mentioned before. And if your gauge group, let's say, is SUN, you always have an SUN global symmetry at weak coupling, because this is basically the symmetry that remains once you move to the boundary. However, this global symmetry has only boundary currents. There are no bulk currents for this global symmetry. If, on the other hand, you have the same gauge theory with magnetic boundary conditions, in that case, electric charges are not allowed in the bulk. There are order 1 degrees of freedom instead of order n square, and in this case, there is, in fact, trivial confinement. Beyond these two boundary conditions, one can discuss more complicated combinations which are associated to subgroups, etc. And also, for if one considers the simplest, let's say, asymptotically free gauge theory like QCD with Dirichlet boundary conditions, you would expect a confinement, a confined phase transition, as it was argued already. And the way that works, which is intuitively obvious, is that if I call lambda the scale that is characteristic of the gauge theory, you can define it even as flat space, then if lambda times the radius of ADS is much bigger than 1, you are in the confining case, and if lambda times the ADS radius being much smaller than 1, you are in the deconfined case. Now, if you had the same theory with magnetic boundary conditions, you would expect confinement at all scales and a free theory of order 1. And this is a kind of trivial confinement because no electric charges are allowed in the bulk because of the boundary condition. So far, it seems from this quick discussion that the only clear criterion for confinement, if you have a gauge theory on ADS, is the order of magnitude of the free energy. That is, whether it's order 1 or order n square when n is large. If n is small, you can't tell much. Of course, one would think that Wilson loops, they would give us information as they do in flat space. However, Wilson loops are more complicated to read in the case where you are in ADS. For example, if you consider large Wilson loops, the area and the perimeter scale are more or less the same in ADS if you are in global coordinates. However, in that case, one may try to use subleading differences, but the subleading differences are not known. On the other hand, it is true that if one puts the theory in ADS on Poincaré coordinates, in that case, there are two classes of loops, and they have different behavior for length and area. However, one should remember that if you put a quantum field theory on two manifolds, that their only change is a change of coordinates, the quantum theories are not the same. Let me come to conformal field theories on ADS, since this is something that has been discussed so far. So, of course, the prime example is n equal 4 super Yang-Mills, and this has been analyzed. There are many boundary conditions. In fact, if you take R4 and you put just a hyperplane as a boundary, and if you ask, if you want to classify the boundary conditions that preserve supersymmetry and to a certain degree conformal invariance, in fact, these have been classified. There are many. And on the other hand, this theory, if you do a conformal transformation, you can turn R4 plus, which basically indicates R4 with a boundary, with a flat boundary, you can turn it into ADS4 in Poincaré coordinates. And in this case, Dirichlet boundary conditions involve non-trivial webs for 3 of the 6 scalars, so they break automatically the global symmetry, and it is known that at weak coupling the theory is generically non-confining, but at strong coupling, some boundary conditions, in fact, induce confinement. And if one uses S-duality, then if you have a theory with a coupling which is much bigger than 1, and the Higgs condensate, as I mentioned, it is mapped to a weakly coupled theory with a magnetic condensate, and this is expected to give you confinement. And in particular, S-duality interchanges, among other things, Dirichlet and Neumann boundary conditions. So with Neumann boundary conditions, no order parameter exists that distinguishes a confining from a deconfining, a non-confining phase. And this is a problem that so far we don't know how to address. So in that particular case, you don't expect, because of this lack of order parameter, a sharp transition between the two phases. And people argued that this is in accordance with the fact that large sushi tells you that you should not have a phase transition. Moreover, if you put any of these theories at finite temperature, their behavior is not understood. Let me now come to a different issue, which is the notion of proximity in quantum field theory. This is a kind of intuitive notion, and basically it's a question, in a sense, how close one quantum field theory is to another. And one way to define this type of proximity is in terms of a landscape of quantum field theories. And this is, of course, a space that's relatively easy to imagine and describe locally, but it is very difficult to control globally. And the same picture, as we understand now, holds also for string vacua, what these days people call the landscape. Of course, AdS CFT suggests that the two spaces are probably the same. And from this point of view, one possible definition of the notion of proximity among, for example, conformal field theories is whether these conformal field theories live in the same Hilbert space. For example, if there is a flow that connects CFT1 to CFT2, then one can claim that the two theories can live in the same Hilbert space. There was another notion of proximity that was formulated recently by Van Ramshog. He called it the CFT masquerade. This is mostly relevant, in fact, for holographic, for theories which have holographic duals. And there are several ways of describing it. One way would be when states of CFT1 can be approximated by states of CFT2. Another way to describe it is, can a suitably chosen state of C1 faithfully encode the space-time that's dual to a state in CFT2? And another way to describe something which looks similar is whether two theories with different operator spectra describe the same bulk geometry. Now, different semi-classical theories of gravity, of course, could be part of a larger non-perturbative theory. And if I were, for example, to draw a picture of this kind of proximity definition, would be like follows. This is a holographic bulk space. Asymptotically, here is the boundary, and this is the region, more or less, that's governed by the ultraviolet physics, let's say, of CFT2, sources, waves, which are associated to operators of CFT2. And the question now is whether, in this particular space, we can have in the interior of the space a region which is, in fact, approximating the dual of a state in CFT1. Now, you can also simplify this and put here a brane that would separate the two periods, and then you can ask whether such a brane would exist. Now, this notion, once you work a little bit on it, is very close to the holographic renormalization group connection that I mentioned before, and in fact, a continuous version of this notion eventually boils down to whether the two theories can be connected via energy flow. There is another way, on the other hand, also to describe proximity. For example, you have CFT1, CFT2, and then you can ask, is there an interface theory which can connect these two theories over a common boundary, which is described here? And if you have a holographic definition, that would mean, in terms of the setup that Takayanagi has described several years ago, to having here a brane that will go into the bulk and separate the two theories. Now, we know of such solutions, in fact, in string theory. These are known as Janus geometries, found first by Perl and Hirano, and they describe precisely interfaces between two different CFTs. So let me now come to the holographic picture, and the natural ansatz metric that I will be using to study these issues is an ansatz for the ground state of some quantum field theory, which lives on AdS, d-dimensional AdS. Of course, the holographic dual theory will be in one dimension higher, and the metric here, where u is the holographic coordinate, is more or less describing this. Zeta, this metric of the slice here, is the theory of AdSd, and then I have a scale factor and the extra holographic coordinate. And a solution of this type is going to be dual to some quantum field theory which lives on AdSd. So if I look at the asymptotics of the scale factor near the boundary, which here in these coordinates is at u equals to minus infinity, they control basically the source of the AdSd metric, and in particular, they control what is the size of the AdS space, or the curvature, if you wish, on which the quantum field theory is described. If your theory is a conformal field theory, in that case, we know the scale factor exactly. It's cos u over L. And in that case, u goes from minus infinity to plus infinity. And in this case, it seems that the space has two AdS boundaries. One is at u equals plus infinity. The other, this is what I call B plus here, and the other is at u equals, minus infinity, and the other is at u equals plus infinity. Now, the metric is locally AdS, and in fact, this type of geometry can be mapped to a global AdS by a large geomorphism. If you want to see globally what this solution looks like, in fact, this is the picture we have of AdSd plus 1, and in this case, the two boundaries are isomorphic to these two half spheres. These are Sd minus 1, I call them plus. This is the upper hemisphere, this is minus, this is at u equals plus infinity, u equals minus infinity, and they intersect here at Sd minus 1, which is eventually what makes the complete boundary of AdSd plus 1. There are similar remarks, in fact, for this is, of course, the picture if you have a Euclidean signature, and similar remarks, in fact, hold for if you have a space of Minkowski signature. Now, unlike the case of non-negative curvature slices, that is when you put a quantum field theory on either a flat or a positive curvature manifold, the negative curvature of the slices here is responsible for the scale factor, in fact, to be not monotonic. This is already seen in the simplest AdS solution. This cos starts infinity at one boundary, goes down to a minimum, and then goes back up. So in the bulk AdS case, if we put a CFT on AdSd, eventually the gravitational solution is interpreted as two copies of the same CFT, one on B plus, another on B minus, and the two boundaries of this AdS, in fact, have a common interface, and they are isomorphic to the equator. And therefore, the interpretation of the holographic solution is two copies of a CFT on AdSd with a common boundary and transparent boundary conditions on this common boundary. Let me now, so this is what describes what we call an interface between two quantum field theories. And let me now come to what would be a wormhole. Now, consider in general, again, an ansatz, as I discussed before, where this slice metric is not necessarily AdSd, but is any metric which has a negative constant curvature. AdS, of course, is one case, but there are many more metrics with negative constant curvature, not globally AdS. And in this case, again, the solutions will be qualitatively similar to what I discussed before. They will have two boundaries, B plus and B minus, at u equals plus or minus infinity. However, the interpretation of the solutions now depends on the nature of the negative curvature manifold that one has here. And in particular, if this negative curvature manifold is compact, like it happens, for example, with G bigger than 2 Riemann surfaces in D equal 2, or Schottky manifolds in D bigger than 2, in that case, these two boundaries don't touch each other. These are the slices and now have finite volume, and therefore the picture is precisely an AdS sliced wormhole. It has two boundaries which are completely distinct, and you can make it, in fact, also Euclidean if you wish. However, if on the other hand the slices are infinite volume, like in the case of AdS, then the two boundaries are not distinct, but they touch each other, and then the picture is in terms of an interface. And in particular, in the conformal case, in which e to the a is cos, in general, u minus some constant u0 over L, you can find that the size, the boundary size of the curvature of the two ADS slices is related precisely to this u0 via this formula. So in this sense, this looks like two quantum field theories on two ADSs, and these two ADSs have different curvatures. Now, if you use as ADS for ADS slice Poincare coordinates, then this is precisely the Janos interface solution, where on one hand you have half of the space in flat coordinates, and on the other you have half of the space in other coordinates, and the common boundary is precisely here. And this is what describes what people call holographic interfaces many years ago. So all of these contexts are basically governed as far as RG flows by the same equations. The only difference is whether the slice has finite volume or not. However, the flow equations are independent of which constant curvature manifold you're putting there. Therefore, the same solutions apply to all of them. So let me now come and study more carefully these ADS slice RG flows. So I will simplify the theory in order to do a better job and also a simpler presentation. I will keep only a single scalar in the bulk, including gravity. I will be in general dimension. This scalar will have an arbitrary potential that I will take it to be negative always, as I want to be always in the generic area in which holography usually works. And I will make the ansatz I told you before. This is a negative curvature, constant curvature, negative curvature slice. This is the scale factor. The scalar will have a profile that depends only on the holographic coordinates. And there is some size to this scale factor here, which is given by the curvature of the slice. Now, if I write the Einstein equations for this, they are very simple. They are written here. I don't know if you see clearly all the dots, which mean derivatives with respect to u. This is the terms that appear here, which are because of the slices. And since I have negative curvature slices, this red quantity r of z is negative. And the same applies here. So these basically are the equations that one would have to solve to find the RG flows. And as I mentioned, for any constant curvature matrix, the equations are the same. And what we would like to do is to systematically study the solutions of these equations. Now, all regular solutions, in fact, can be shown to have generically two boundaries, which I will always call B plus and B minus, and they will be always at U equals plus and minus infinity. And both of them, they be conformal to the slice geometry. The endpoints will be extrema. I call them phi plus and phi minus of the bulk potential that I will show you in an example later on. And the associated CFTs that are associated to the two boundaries, I will call them CFT plus and CFT minus. And every solution, which means a solution for the scale factor and scalar for these equations, would correspond to a wormhole solution if my slice is compact, and this wormhole will connect CFT plus to CFT minus, or an interface solution if M is non-compact, and in this case, the interface B plus together with B minus would be corresponding to the interface between these two CFTs. So in pictures, this is what the solutions would look like. This is one boundary, let's say, on U equals plus infinity. This is the other boundary at U equals minus infinity. And in general, the scale factor will start at infinity, go down to a minimum. This minimum will always call it A bound, so it's important to remember this work in order to understand the rest I will be saying. And so I will always have this, this shape, but then phi can do different things. It can be monotonic, it can change monotonicity, etc. For example, in this case, it can bounce around and go back to the same value as it started, and this would correspond to the same CFT, but probably with different parameters. And if I look in this scale of in a picture in which here is phi and V is the potential, this would be a solution which corresponds to the maximum, that's a CFT, which goes away and then comes back to the same CFT. And I could have also solutions where phi starts from a maximum and then goes to another maximum of the potential, and then this is a flow from a CFT to a very different CFT, and these two CFTs correspond to these two distinct maxima of the potential. So I would like to stop here and see if there are any questions.
There is a question in the chat, Elias.
Let me see.
The metric one is a flat slice of the ADS?
Of the ADS. Now, I'm not sure which is metric one. Let me go back. Is it here that you are referring?
Maybe yes.
In any case, this slice here is always a constant negative curvature manifold. It could be an ADS, and you can write it in any coordinates you want. You can write it in correct coordinates. You can write it in global coordinates. As I said, the quantum field theory depends on which coordinates you choose in general, but not the flows. The flows don't depend on what kind of metric you have, provided it has constant negative curvature, and don't depend whether this manifold is compact or not compact. Eventually, the physics you will calculate, they will depend on that. I don't know if that answers the question. Can you type in chat?
Okay. Any other question?
Okay, I see nothing.
Okay.
So let me move on and describe suppose one finds such a kind of flow. How does one read the couplings of the two quantum field theories that are associated with this flow? Because as we've seen, these flows have always two AdS boundaries, and therefore each boundary has its own couplings read from the sources near that boundary. So let me call the two boundaries initial and final by choosing a direction for the flow, although this is a choice. So in all cases, the metric asymptotes to the metric I chose for the slice. And the only parameter, of course, of this metric is its curvature. So if I look at how phi basically asymptotes as u goes to minus infinity or plus infinity, which are the two boundaries, this is the usual exponential behavior, and then the coefficient is basically the source for the scalar, or if you wish, the coupling associated to the scalar operator, which is dual to phi. And therefore, each of the two quantum field theories will have a coupling that you read around the appropriate boundary, phi I minus and phi F minus. So these are the couplings, and therefore, each of the two quantum field theories has two dimensional parameters. The curvature of the AdS space on which it's living and the coupling with which it is perturbed. Both of them are dimensional, and from these, so I have 2 plus 2, and from these 4 dimensional numbers, by making ratios, I will make 3 dimensionless quantities. One is on each side the curvature divided by appropriate power of the coupling, Ri and Rf, that's the dimensionless curvature, and then the ratio of the two couplings of the two theories, which also is dimensionless. And in a sense, these are the true parameters of the solutions and the theory and the dual theories that they describe. So let me, in order to solve them, one needs some formalism. This is the so-called first order formalism. So I define superpotentials in the standard way. A dot basically is defined to be W. It's a function of phi. And phi dot is defined to be this function S of phi. And then this curvature-dependent coupling I define to be T of phi. And then I can convert my gravity equations into equations for these three functions. And one of them, you can solve it algebraically. So once you know W and S and the potential of your gravity theory, you can compute T. And then W and S satisfy these two first-order equations in terms of the potential that's given. And if you solve these two first-order equations for W and S, then you can integrate easily these equations and find the full solution. So let's understand a little bit the integration constants of these equations. So when the curvature of the slice is positive, for example, if slices have spheres, then the flows describe spaces which have a single boundary, and this is dual to a single quantum field theory with a relevant coupling. And in that case, the equations have, as here, three-dimensionless integration constants. One corresponds to the dimensional curvature of the quantum field theory, and the second corresponds to the dimensionless scalar wave. And this wave, as everybody knows, in that particular case, must be tuned for regularity and becomes, in fact, a function of this source parameter R. The third one is not physical and can be removed by a radial translation. Now, if you look at the first order formalism, here we have two integration constants, and it's easy to show that one of them is this dimensionless curvature R, this is a source, and the scalar wave, which is a wave. And therefore, the scalar wave is a function of the source. So then this function T that I defined before is determined uniquely, and from this you can determine the scale factor as a function of phi. So the first order equations, in fact, have more integration constants, but these are related and don't give you any more relevant integration constants. But the point is that in the case with positive curvature, which I'm not discussing here, but has been discussed in the past, basically you have one independent relevant constant R, which is the dimensionless curvature, and then the wave is a function of R. Let's see now what's different here. The number of integration constants, of course, the bulk equations are the same, there are three. However, the big difference here is there is no regularity condition because the manifold never swings to zero. And in fact, it can never swing to zero because this is never regular. But it bounces and becomes infinite again, and therefore there are no regularity conditions. Therefore, the scalar wave is an independent parameter and doesn't depend on R. So, of course, one constant is redundant as usual, but the other two parameters are independent. And they can be now interpreted in terms of the two boundaries that one has. So the two-boundary solution has two dimensionless independent parameters. But as you remember from our discussion before, this is one less from the three parameters I would expect from the dual quantum field theories. However, the extra missing parameter, I will add them later on. And for the moment, we will have to stay with these two parameters, which you can take them to be the dimensionless curvature of the two boundaries. So let me now describing how you classify the possible solutions. And to do this, since it's based on numerical work, I will have to pick up a representative potential. And for this, I picked up phi4 potential. It has various parameters here that look a bit bizarre, but basically don't look at these formulae because they're not important. Let me describe in words. In fact, let me show you first of all potential. It's a potential with two maxima and one minimum. The maxima are UV fixed points in the usual sense if you had flat flows, and the minimum is a IR fixed point. And I will put the left maximum at phi equals 0. The right maximum will be at some value 8 point something, and then the minimum is somewhere in between. And then I will fix the scaling dimensions of the operator dual to the scalar phi in these two maxima. One will be 1.6, the other will be 1.1. I fix also the AdS scales here and there, and that's basically what fixes completely the potential. So this is the type of potential. It's a generic potential with two maxima and a minimum, and this is what I will use, in fact, to study the flows of the type I've described here with negative curvature slices. Now, let me make some technical definitions first. As I mentioned, when I talk about an A bounce, I mean a point where A, which is the logarithm of the scale factor, changes direction. That is, the scale factor from decreasing becomes increasing and vice versa. That corresponds to A dot equal to 0. It means that the superpotential W is exactly 0 at that point. And as I mentioned, there would always be one such place where the scale factor turns around. And this is because my slice curvature is negative. So all our solutions will have a single A bounce, and the position of this A bounce I will denote by phi 0. So phi 0 from now on means where the scale factor bounces. I will also use the word phi bounce. Phi bounce is a point where phi turns direction. Phi dot is equal to 0, which means my function s, which is equal to phi dot, is equal to 0. And it's a point where, of course, the first order equations break down, but the second equations do not. So I don't worry about this. And finally, I will use the word IR bounce to mention a bounce which is both at the same place, an A and a phi bounce. That is, both A dot and phi dot are 0 at the same place. So this is a definition, and I should say that all of these definitions are defined away from the extremal points of the potential. So let's now see how we will solve our equation. I will always start from the unique A bounce that our solutions have, and this happens at phi 0. So phi 0 is one of my parameters of the solution, and then I will solve these two first-order equations. To solve them, I need one more initial condition, and this initial condition is the value of s at that point. So once I have these two conditions, more or less I can find, in principle, by scanning over them, all possible solutions to the system. So this is the complete initial data for my system. For each value of phi 0 and s0, I have a unique solution, and then the way I solve is I start and solve on the left using these initial conditions. I also solve on the right with the same initial conditions, and this completes the full solution, which will reach the two boundaries or the two sides. And then once you have the solution, you can calculate the curvatures from the standard formula I showed you before. Now, before showing you what the solutions appear, I have to also give you one more reminder of a few things we know about general properties of holographic RG flows. So, first of all, it is known that near a maximum, the potential has always two branches of solutions, which are known as the plus and the minus branch, and basically they depend on whether A dot depends on delta plus and delta minus. And the minus branch is the generic branch. It contains the generic solutions, and it contains two arbitrary integration constants. The plus branch contains only the special solutions for which the source vanishes. In fact, they correspond to relevant wave-driven flows, and therefore it contains one less integration constant, and that's why it is tuned compared to the minus branch. That's important to remember. Now, for both types of solutions, if you are near a maximum of the potential, the metric has an AdS boundary, and the scale factor has a maximum. Now, I will denote such asymptotics by max to remind you that I'm at the maximum of the potential, and plus and minus to remind you which of the two solutions I am picking. Let me go now near the minimum of the potential. In that case, I also have the plus and minus branches. The minus branch is again the general solution. It has two integration constants. However, it does not exist if the slice has non-zero curvature. It exists only if the slice has zero curvature. That is, it's flat. And in such cases, it describes the well-known infrared end of the energy flow, the flow that stops at the minimum. There is another less well-known branch of solutions, which is the plus branch. This is a special solution again. It contains one less parameter, and in fact, in such a case, the AdS metric that you compute has an AdS boundary near this solution and not the interior of AdS. So this solution, in fact, describes a UV fixed point. And in particular, this UV fixed point is driven by the VEV of an irrelevant operator. And such a solution can exist in general both for flat and curved slices. So these two solutions have different interpretations. This is an infrared end of the flow. This is a UV driven by an irrelevant VEV. Let me call these two solutions near a minimum, min for minimum, and plus minus to remind you which one of the two it is. So let me now write what are the possible flows. Basically, we remember that max plus minus at the maximum and one of the minimum solutions are associated to AdS boundaries and therefore describe QFTs at UV fixed points. And minimum minus is a shrinking geometry and describes therefore an infrared fixed point. The plus branch solution, plus here and plus here, contain less integration constants and exist only in fine-tuned cases. And the minimum minus solution does not exist when the dimensionless curvature of the slice is non-zero. These are general properties one can derive from the equations I showed you. So by putting together these endpoints, now one can classify complete flows. And let me do that for you. First of all, let me start from the usual flat slice flows that everybody knows. In this case, you have 4 combinations because of these 4 endpoints. Max minus min minus, max plus min minus, max min plus min minus, and also another one that I will describe. However, all of these 3 here are UV fixed points, and this is the only IR fixed point. So these are the only combinations that in flat slices, in fact, correspond to flows. As I said, this is a general flow driven by a relevant operator. This is a flow driven by the VEV of a relevant operator, and this is a flow that's driven by the VEV of an irrelevant operator. Are there questions so far? I see already a question here, whether the potential I showed you generates confinement. The answer is a no, because I will consider flows that end at minima and maxima, and therefore they will end in AdS, and therefore there will never be confinement in this. The confinement issue is very interesting, and it's something we're studying now. Are there other questions? Okay, let me move on. Suppose now that you have quantum field theories with on manifolds with positive curvature, like spheres, for example. In that case, although the flows can start at the extreme of the potential, and therefore all of these 3 endpoints which correspond to UV fixed points work, they cannot end at minimum minus at the minimum. However, they can end at any other point of the potential they want in a regular way. And in this case, all the flows are classified by starting at maxima or minimum, but with these flows, and ending anywhere else. And then finally, let me come now to the case in which I consider here, which is R being negative. Now, as I said, it is not possible for the flow to be regular and end at intermediate points. The reason is that there is basically, when AdS space slice shrinks to 0, it can never do it in a regular way. So that's not allowed. Therefore, all the regular flows must end at the extreme of the potential. And basically, as the asymptotic solution, which is min minus, does not exist when the curvature is not 0, I have to forget about this. And then I'm left only with the other 3. And if I put 3 times 3 with the start and the end of the flow, I get all of these possible flows that I can have. I have max minus max minus. This is the generic flow, 4 integration constants. 2 here and 2 here. Then max plus max plus. This is 1 here, 1 here. This is maximally tuned. And then I have all the other combinations in between. Now, this is the only one that's not tuned, and therefore my generic solution will be here. All of these contain always max minus, so this is not tuned, but the other point is tuned. So these will be codimension 1 in the space of solutions. And then I have this and this, which are codimension 2, because they are tuned both at the initial point and the final point. And in fact, we will see that all of these solutions, we will find them. There is one more solution, which is max plus min plus, which is fine-tuned. No, I'm sorry. This is, as I said, fine-tuned. But there is one more solution which is fine-tuned, but we will not find it. This is min minus min plus, min plus min plus. And the reason we don't find it is because our potential has one minimum. If it had two, I think we would find also the solution. But all the other solutions, in fact, we will find them in the space of solutions that I will be studying here. So let me, in fact, show you, first of all, the moduli space of solution and explain it a little bit. So this is S0, that's one of the integration constants. And this is phi 0, that's where, in fact, the A bounds happens. And as I argued already, in terms of these two real integration constants, I can classify all solutions. For each point on this diagram, there is a single solution. So let me explain here the colors. This region, first of all, let me say that every solution has an equivalent solution by taking S0 to minus S0. And basically, it corresponds to interchanging the two endpoints. So basically, the dependent solutions are really everything that's with S0 positive. So let me first look at this orange part. This is a set of solutions which, in fact, by reading these two numbers here, the first number says how many A bounces there are, and the second how many phi bounces. So this means a single A bounce. In fact, all our solutions have a single A bounce. In fact, you can see it maybe here. See, no. You can see here A is always of this type. In one boundary, it starts at infinity, goes down to a minimum, and then goes back to infinity at the other boundary. All solutions are like this. So here, A bounds, but no phi bounds. Let me show you an example. Basically, you start at this. So remember, the potential has one maximum here, the other maximum is here, the minimum is here. So you can start, for example, at this maximum, and then you can have a solution, let's say this one, which goes to the other maximum. So it goes from left to right, two different fixed points, and phi always increases. So no phi bounds and one A bounds. All the solutions have one A bounds. So all of these type of solutions are precisely in the orange part. Then there are these two green parts, and here you see 1, 1. One is an A bounce, but here you have a phi bounce, and these start from one maximum and they go back to the same maximum. So let's go and see an example. So you see this solution starting from this maximum, going around here, and then coming back here to the same maximum. And of course, you see that phi increases up to here and then decreases. So it has a single phi bounce. So all of these types of solutions are in the green. And then these have, again, go from the same to the same, but they have two phi bounces. So let me show you an example. It's like this green solution starting here, going in this direction, turning around once in phi, turning another time in phi, and then ending up at the same fixed point. So these are the blue solutions here. And then these are the red solutions. These are 1, 1. So they go from left to right maximum, but then they have a single phi bounce. So let me give you an example. So the example is this blue. Starts on this, bounces once in phi, and then goes all the way here. Of course, there are parts here which are written in white here and also here. These corresponds either to solutions that have more phi bounces and eventually to solutions that are singular, that go off to infinity. But we will not look at these solutions. Other questions? So let me now, so for each of these solutions that one finds numerically, one can calculate the data of the solution. For example, can calculate on one boundary what is the dimensionless curvature, and on the other boundary what's the dimensionless curvature, r left, r right. These are the only parameters that these solutions have, and this is, for example, a plot where one is choosing varying S0 for fixed phi 0 here, and one gets this line, and then for this variation, for these different solutions, gets this line, and eventually one, of course, can fill the whole diagram. This is straightforward to be done by looking at the solutions and reading the asymptotic data, which determine, of course, the boundary theory. So let me now go and describe the boundaries of the regions that I've shown you, because the boundaries are precisely places where the nature of the solution changes. And in fact, they can be identified with the special solutions I made before. If you look, for example, in the solutions that go from left to right, which are inside here, any solution inside here is a generic solution. It's a max minus in the notation I indicated before. But once you go to the boundaries where they change to other types of solutions, there is one single tuning. For example, on this boundary, one of the endpoints becomes max plus. And the same in this case, this remains generic, but this becomes min plus. These are tuned solutions. And then, as you can probably expect, if you go to the corners here, the solutions, in fact, are fine-tuned, both of them. And for example, at this corner, you can check that you have a max plus solution, and this is codimension 2 in the space of all solutions, as is expected. So beyond, of course, similar things happen in other parts, but I will spare you this. Although these are curiosities, of course, and they show that all solutions in general can appear, some of them, in fact, present some new phenomena that at least I personally have never seen in such solutions. And the new phenomena is what we call flow fragmentation, walking, that is very slow running of the scalar, and emergent boundaries that come out of nowhere. So let me show you an example of this. And in fact, it is a solution which interpolates. In fact, it's a solution. Let me show you. It's a solution that corresponds to these blue boundaries here. Remember, this is a solution that goes left to right, nothing special. And this is a solution that instead of going left to right, turns around and goes back to left. So let's see how this can happen once you approach the boundary in which such a solution has to become this, and vice versa. So here I show you two solutions and how basically they go. Look at this solution. This solution starts here, comes very, very close to the minimum. This is the left maximum, the right maximum, and then turns around and goes back to the same maximum. And then on the other side of the boundary, it's a solution again starts from here, goes a little bit on the other side, and then goes to the other maximum. And then by continuity, you would expect that as you approach the transition, you would have a solution that in the end will come down exactly to where the maximum is and will go either here or here, depending on which limit taken. Now, this is a solution on one side that I drew here. This is the limiting solution. Now, this solution is the sum of two solutions. In fact, this solution here starts at this maximum and ends at the minimum, but this ending at the minimum is allowed only if you end up with a plus solution, and then this is a boundary, because minimum plus solutions are boundaries. And then this solution starts at this, again, boundary, and ends up here. And again, this is forbidden to do that, but this ends up at the minimum in a different way. The associated curvature of that solution is 0, and then this ending is allowed. So this is a sum of two solutions, and now you have one boundary here, one boundary here, and one boundary here. So let me show you what it looks like, in the limit, of course. In fact, let me show you the plots. For example, this is the u-coordinate. The u-coordinate starts here, goes to minus infinity, then comes here. Then it's getting stuck, and you see that as long as this goes up, phi doesn't move. This is the working part I told you. And as you approach the boundary, this line moves more and more up, and the walking becomes more and more prominent. And of course, the same thing happens as you see here. You have a scale factor going down, going here, and then going up, and then going back to the boundary again. But then this piece will become very long in the limit, and this will generate a new boundary in between. Let me show you a little bit the topology of what it looks like. You started with a solution that looked like this. And in the limiting case, you get a solution which is a normal one where this shrinks. And another one which has, again, two boundaries. So this is what I would call, first of all, solution fragmentation, which we have seen also in other examples, but the generation of a new boundary in the limit. I don't know, there must be an algebra for such degenerations, but we don't know it, we don't understand it yet. And I don't know if these solutions mean something more for holography, and in particular for the interpretation of wormholes, but that remains to be seen. So let me quickly come and remind you that, as I said, I found 2-parameter solutions, but I expect 3-parameter solutions. The third parameter, in fact, can be introduced in a very simple way. You just take a 2-parameter solution, you cut it in two, and now you glue it with a translation on one of the pieces. And what this does, you can do it, in fact, so that all the parameters are continuous and the equations are satisfied. But what this does is it takes the ultraviolet parameters of one boundary and it rescales them by conformal transformation. And this generates, in fact, the third parameter. And now you have completely described all the theories you would expect in this class of solutions. There is one more thing, in fact, to describe here. All of these solutions have two boundaries. However, we started by trying to ask the questions. What happens when I have a single quantum? And therefore, these solutions describe either wormholes or interfaces, depending on what kind of slice you get. But how can you describe a single quantum field theory on an AdS space? So far, the only way we know is to take a single boundary solution which is symmetric and orbifold it. This can be done basically in a class of solutions we call S. These are the solutions that have S0 equal to 0, one of the initial parameters being 0, because these are completely symmetric. And in this way, in fact, once you orbifold, you will get U now that goes from minus infinity, a single boundary, to some U0. And you can interpret, in fact, this as an end-of-the-world brane at A0. However, because in this place, this is an infrared bounce, which means both A dot and phi dot is 0, the brane you have to put there is both tensionless and chargeless with respect to the dilator. However, if you put, for example, a CFT and you make this orbifold on AdS, what you will realize is that conformal invariance is broken. For example, in the two-boundary case, if you look at 2-point functions, you have 4 options. You have a 2-point function where you put one operator, both operators on one boundary, both operators on the second boundary, or one operator in one and one operator in the other. This is what is meant by G++, G+-, etc. And if you compute, for example, the symmetric orbifold on AdS for the CFTs, in fact, G, the 2-point function now is G++ and G+-, which is given by this combination where cos L is the usual distance in 1 plus the usual distance in AdS space. And in fact, this is not conformal. If this was only this, it would be conformal. Now, the interpretation of this would be that the boundary conditions which are involved, because you have a single theory on AdS, somehow break conformal invariance. If, on the other hand, you wanted to insert a brane at U equal U0 and impose Dirichlet boundary conditions, you would obtain the same result, but then you will get a minus sign here. And in fact, this would correspond, in fact, to Neumann boundary condition. Now, you can ask the question, are there other boundary conditions that you can put on the brane in order to get the conformal result? The answer is yes, but this will be generically non-local on the brane, and I don't know if this is a relevant option or not. So this remains for the moment. So let me quickly conclude. We have studied RG flow solution with slices that have constant negative curvature manifolds. Such solutions have generically two boundaries and can be interpreted as wormholes or interfaces. We have analyzed in detail the simple example. The results suggest that proximity is very close to RG flow connection in terms of interfaces. We have found also exotic limiting cases where one obtains all possible exotic RG flows. And other phenomena that we found include flow multifragmentation, working behavior, and the generation of new boundaries. And we have defined single boundary solutions via orbifolding and used the bulk end of the world brain. However, all of them seem to give non-conformal correlators. There are many open ends, of course. The case of constructing a single holographic theory ADS is still open, in my opinion. The exploration of larger regions of the scalar manifold is important in order to see how local the proximity of such solutions is in field space. The issue I raised in my introduction about Wilson loops is currently under study and needs to be understood. Finite temperature effects are interesting but not understood. The fate of the incident gas on ADS can be studied, in fact, using holographic methods and will be done. Entanglement in single theories as well as interfaces is interesting in order to decipher what it says. And I should mention also that the computation of interface correlator for interfaces is an open problem. Thank you very much.
Thank you, Elias. Thank you for your nice talk. There is one question by Fabiano. If you can please.
Yes, let me read it. I have a question about the theories beyond Einstein's gravity, like Hornetsky's gravity, for example, using the J. Horn, I'm not sure, sector in this theory that considers a product coupling between the scalar field and the Einstein tensor. If you start modifying, the question is about modifying the scalar theory by adding higher derivative interactions, but not just any higher derivative interactions, but those seem to give you second order equations. In general, although this is very popular among people who do cosmology, from a holographic point of view, one can at best see them as laboratories for what can happen in higher derivative theories. However, one should remember that always these higher derivative theories their effects must be small compared to the leading result. Otherwise, they are not trustworthy in holography and in string theory. So therefore, yes, you can use them to describe RG flows. You will find probably things that cannot happen in the two derivative case, but you cannot always trust what you find that these will happen, let's say, in top-down situations, but only those that have a smooth limit when you turn off the higher derivatives. That's all I can say at this stage. Of course, this issue has been done in the past, especially in holography and applications to condensed matter, but always it should be used with the caveat that I mentioned.
Okay, thank you, Elias, for your talk. Okay. Is George in here? Can you, George, share your file?